Welcome back to Physics for Future Leaders and our discussion of climate change. And the first thing that we're going to talk about today is albedo. So this one right here, first boxed one in the list. And remember that we define that as how much solar radiation gets reflected from the Earth. So not absorbed and reabsorbed via the greenhouse effect or anything like that, but just bounced right off of either the atmosphere or the surface of the Earth. And that's one of the effects, right? One of the drivers of climate and climate change. So let's see what we can say about it. Okay, so the top thing here just lays out the definition, and the takeaway for the Earth on average is about 30% of the total incoming energy from the sun gets reflected before it is ever absorbed by the Earth and contributes to the heating of the planet or anything like that. So if you look at this diagram that someone kindly made for us, you've got incoming solar radiation. So right here, so on the left, we have about 341 watts per square meter coming in from the sun. And that amount is based on both solar output and how far we are from the sun, etc., etc. Okay, but on average, about 341 watts per meter squared. And that energy flow goes a whole lot of different places. We're not going to talk about all of them. We're going to talk about the ones that relate to albedo, this reflection of solar radiation. So you can see that right here, we've got an energy flow where just the clouds in the atmosphere, as well as the material of the atmosphere, all the gases that make it up, reflect a certain amount of that incoming energy. So 79 watts per meter squared out of the 341. But that doesn't quite get us to 30%. Then we have to look at the stuff that comes down here to the surface of the Earth. And you'll see that a smaller amount, though still significant, is reflected by the surface. And the amount that's reflected by the surface is depending on what surface it is that is hit. But on average, over the whole globe, you're reflecting about 23 watts per meter squared of the incoming solar energy right back out into space. Okay? So that gives us this total 102. If you do the whole calculation, it's not exactly 30%, but as close as makes no difference. All right. So, by the way, if you want to further examine this diagram, it's a good one. It shows you a lot of the major effects and sort of absorbing and re-reflecting stuff. So all of the greenhouse gas effects that we're seeing over here, and you see that the total outgoing long wave radiation, so that's stuff that is, what they mean by long wave is sort of long wavelength in the infrared spectrum. So not long wavelength like radio waves, but long wavelength infrared, which is basically just heat, low quality, not low quality, but low energy heat. Okay, so albedo. We have this 30% that just gets bounced right off of the Earth and back into space. But of course, the amount that gets bounced is dependent on, well, whether there are clouds, whether the ground is ice, or whether it's hitting the ocean, or whether it's fresh, new white snow, or whether it's old, dirty brown or black snow. All of these different things can change the number in these flows that's being reflected at the surface and back out into space. And that also can change just how much heat is being absorbed by the Earth, and thus change how much our temperature changes as a result of this absorbed energy. So if we're looking at this picture, and apologies for the slightly washed out colors here, but if you look way down here at the bottom, okay, what you're looking at there is, in the color of the diagram, the change in reflectivity as a percentage. You'll note that it only goes as high as 8 and as high as +8 and as low as -8. And so these are relatively small changes over time, but ones that are important. And this is over maybe a 10, 15-year period. Okay, so it's not over a really long time. And the way that this is measured is we have a whole network called Ceres, or Ceres, I believe it is, measuring the reflected light from the Earth's surface and Earth's atmosphere, right? So the sunlight comes in, it bounces off. We have a bunch of satellite sensors that are tuned to look at how much solar radiation is just being reflected right off the Earth. And we can build maps like this. You'll notice that there's a lot of variation over the globe, and that's due to changes in cloud cover, changes in the amount of ice and snow there is. You'll notice, for instance, in the Arctic region, that's one of the regions that is most affected recently by the changes in albedo. And if you think about that for a moment, assuming you pay attention to the news, you can probably understand that the reason that the reflectivity, the albedo of the North Pole and the Arctic region in general, has gone down, it's not reflecting as much solar radiation, is because there is less and less ice over the course of a year at the North Pole. And that's largely due to global warming, this climate change that we've been talking about. Now, over the rest of the globe, the patterns are much less clear. So you can see in Antarctica, some regional things here, so small drops in reflectivity, that's certain ice sheets collapsing and floating off into the ocean. But then in other parts, it's actually gone down because of the buildup of ice and snow. So at the South Pole, the picture as far as average albedo, and then thus how much we're reflecting, versus how much we are absorbing, is much less clear. Okay? So if you average over the entire globe, so changed a lot regionally, but very little globally, small, tiny effects, but not a huge one in terms of a driver of climate, surprisingly. Now, if you imagine back to the Ice Age, sort of an ice ball Earth scenario, albedo would be more like 0.8. So 80% of incoming solar radiation would be reflected by the atmosphere and the Earth's surface, and that's because ice is very reflective. It bounces a lot of the incoming visible and infrared light right back out into space. And so that kind of scenario is, if we're cold, we're going to get even colder because of all of that extra stuff being reflected because of the presence of ice and snow. You can imagine that, going the other direction, that if we have less and less and less ice over the globe, and we're seeing this, at least, remember, regionally in the Arctic area, though less strongly anyway in other places on the globe right now. But in the longer term, if we continue to have this run-up in temperatures, we could have a real problem, because in addition to the North Pole and the Arctic region there, Antarctica and various other places where there's a lot of ice, like Greenland, could change from having a very high albedo and reflecting a lot of energy for us and keeping that energy from heating the planet, to a situation where we have less ice and less reflectivity. The oceans, for instance, open ocean, absorb a lot of solar radiation. Its albedo is down around 0.1 on average versus 0.8 for ice. If we run into that scenario where we have very little ice anywhere on the Earth's surface, we could have a situation where instead of the ice ball Earth scenario where albedo helps drive temperatures down, we could have a situation where the relatively lower albedo as the ice melts causes more solar radiation to be absorbed and causes a further increase in global temperatures. So, something to think about. Next time, we'll talk about our second factor in driving driver of climate, which is solar cycles. I will see you then.